So, in the earlier class, we had discussed about magnetic micro actuator for different micro robotic related applications. In fact, we had discussed about the different types of magnetic micro actuators, which are available, functionality of different magnetic based micro actuators and its suitable applications. We have also discussed about the different configurations of magnetic micro actuators, how are they microfabricated, and then since it has a potential applications in biomedical, so we have gone through the entire spectrum of these magnetic micro robotics for biomedical related applications. Okay, now we started with piezoelectric related actuation. So we gave a brief overview of we had a brief discussion about this piezoelectric related thing. Some of the key fundamental with reference to piezo actuation is concerned. So the piezo actuation is classified into two. One is called as a direct piezoelectric effect and the other one is called as a converse piezoelectric effect. So in the case of a direct piezoelectric effect, when a stress is applied on certain crystals, we observe an electric movement in the crystal whose magnitude is proportional to the applied stress. This effect is known as the direct piezoelectric effect. However, in the case of a converse piezoelectric effect, when an electric field is applied on a crystal having piezoelectric property, the shape of the crystal changes slightly. This effect is known as a converse piezoelectric effect. So, ideally, with reference to functionality perspective point of view, these direct piezoelectric effect are identified or used as for sensing related applications, and these converse piezoelectric effect are used for actuator related applications. So, based on the domain and based on the displacement appropriately, the overall either it can be used for a micro level or it can be used for a macro level. Whereas, when we try to consider these piezoelectric actuators on a macro level, then we may need to integrate an appropriate stack into the system to increase the overall perspective of this piezoelectric actuators. Now, let us see some fundamentals of these piezoelectric actuators or the piezoelectricity. So, like as far as these piezoelectric actuators are concerned, so these piezoelectric ceramics are being efficiently used. Consider now a piezoelectric ceramic of thickness E subjects to an electric field capital E. So, the electric field E is equals V by E, that is V is the voltage created by the electrical source across the ceramics and the E is the thickness. Then this is in the case of inverse polarization, so that the ceramic is subjected to a deformation induced by this effect. The expression for which is a function of the applied electric field E, which is represented in volt per meter, and S equals E dot D. So, S is the capital S is the deformation produced by the piezoelectric effect, D is M by V, which is nothing but the piezoelectric deformation constant. Now, as far as this mechanical deformation is concerned, nevertheless this deformation is not the only one undergone by the sample. Other deformation must also be considered, which are due to various mechanical forces. When these are induced as well, we obtain an expression for the total deformation undergone by the sample in the question. So, like S equals D dot E plus S dot T. So, the capital S corresponds to the total deformation, D corresponds D dot E plus S dot T, where S is the small s is the elastic compliance, the inverse of Young's modulus of the ceramics, and capital T is the stress resulting from an external force on the sample. Now, when we try to consider the electrical displacement, the piezoelectric materials are dielectrics. Because of this, there is a displacement of electric charge which will call the charge density in the dielectric whenever it is exposed to an electric field. Thus, in the case of a sample, so the expression for the electric displacement in the sample is D equals epsilon E. Epsilon is nothing but the dielectric permittivity of the ceramic of the order of 10 power minus 9 to 10 power minus 12. The piezoelectric material would be subjected to an external force, thus generating an electrical displacement through the direct piezoelectric effect, whose expression is proportional to the applied stress T. So, D equals D dot T, D is the units C by N or V per M square. Therefore, the expression of the total electrical displacement in the piezoelectric material is D equals epsilon E plus D dot T. We can write S and T in the matrix form such that S by D is S D D epsilon and T, if which is represented over here. If D equals 0, no coupling between the electrical and the mechanical domains. So, we will just have an expression for a deformation and an electric charge displacement as would be found for an arbitrary material. This coefficient D is therefore what defines the piezoelectric character of a material, in particular the strength of the electromechanical coupling within it. So, the larger is the D, stronger is the coupling, and the piezoelectric ceramics are three-dimensional. Therefore, we need two pieces of information to describe each vector: the phase to which the factor is applied and its direction, that is V equals Vig, I is the phase of the vector is applied, J is the direction of the vector. So, the symmetry condition on the stress in a material implies Vij J equals Vji. So, for simplification notation for symmetric conditions, so this is a kind of a notation which is a kind of a generalized form which is available, and the overall equation, generalized 3D space equation, is represented in the following form. Now, constitutive equation, these are some kind of generalized equations or generalized parameters which we consider with reference to a general piezoelectric structures. However, when we try to consider a constitutive equation of piezoelectric actuation, so we have a strain Sij which is represented as dkij ek plus this particular equation, and electric field is represented as di, where Sij is the strain tensor, Eij is the elasticity, Ejk is the dielectric tensor, Tkl is the stress tensor, and Dikl is the piezoelectric tensor which is available. Now, as far as this generalization is concerned, let us consider two special cases of this system. One is a kind of a short circuit case where the electric field is applied to the piezoelectric material is 0. We can then rewrite the expression for S and D as shown in this equation. However, in the case of an open circuit case, the displacement of electric charge in 0, we can rewrite the expression of S and D, which is represented over here. A difference between the elastic compliances in the short circuit case, which will be written in the open circuit, which we can write it as S power D. The short circuit case is S power E and the open circuit case is S power D. So, we can conclude the strength of the electromechanical coupling, which depends in practice on the value D. So, we can represent it in the general form. Now, as far as this piezoelectric actuation is concerned, the concept of poling will try to participate in this. So, this poling process is an essential step in the piezo manufacturing. So, it is important to understand the principle as it conditions the material behavior. It is helpful for tuning the material based on our requirement or based on the overall functionality. So, the PZT are ceramics formed of multiple domains before polings. The domain that define a local polarization are randomly oriented and the overall average polarization of the material is 0. So, before the poling, the domains are not aligned. However, after the poling, these domains are aligned. After removing, the polarization are in tension, which is helpful for appropriate applications and to molding it with reference to the functional characteristics. So, during the poling process, a high voltage typically in the order of 0.1 to 1 kilowatt per mm is applied to the material at a temperature close to the Curie temperature, where the transition is ferro-paraelectric is observed. The strong electric field and the heat applied to the material cause a reorientation of the domain towards the direction of the electrical field. A maximum net polarization is then obtained for the crystal. Upon cooling, the thermal relaxation process induces a diminution of the crystal, which will result in the net polarization. So, these are some of the different steps involved in the polarization activities. As far as a strain response as a function of applied voltage is concerned, the butterfly curve is considered to be one of the key characteristics for a piezoelectric domain to investigate, to quantify the piezoelectric domain. So, in order to quantify this piezoelectric structure, so ideally the plot is oriented between the strain with reference to the voltage. So, in order to examine the behavior of a piezoelectric material submitted to an electric field, we assume that the electric field to be aligned along the polarization direction, and we examine the evolution of the strain upon the modulation of the voltage. After the poling process, domains are oriented along a preferred axis, point A on the curve. Lowering the voltage down to point B, we find a pseudo-linear regain that corresponds to the piezoelectric strain response of the applied field. Now, once the voltage is further lowered and becomes a negative, the strain follows the direction of an applied electric field until point C, where the domain starts to reorient in the electric field. We switch to point D, where domains are fully reoriented in the direction of the applied field. If we increase again the voltage up to positive values, we find a symmetric behavior which is so called as a butterfly curve. Now, one of the major issue with reference to piezoelectric structure is these piezoelectric actuator exhibits a kind of a nonlinear behavior, and their characteristics exhibits a hysteresis. So, when we try to plot a curve with reference to displacement and voltage, we can easily observe that there is a kind of a characteristics which exhibits, which will lead to a kind of a hysteresis in the particular process. So, these hysteresis will have, it's a kind of a defect which will try to impact the overall performance on usage of these piezoelectric structures for different functional applications. So, in order to overcome this, so one of the important aspect what people used to do is, like, they used to add a kind of a supporting layer, like which we had discussed about this unimorph and bimorph concepts. So, these unimorphs and bimorphs are well integrated with these piezoelectric structures, so that appropriately the hysteresis can be considerably reduced and it can overcome the overall hysteresis, and it can be used functionally for different applications. Next, when we try to talk about the piezoelectric actuation with reference to creeping behavior, if a constant voltage is applied to the material, the strain tends to drift over time, and an empirical law used to capture the drifting effect is shown here. So, the key parameters which are involved in these drifting effects are: a constant voltage is applied on the actuator, leading to an elongation of del L. The time dependent drifting is captured by a logarithmic law that describes the behavior of the material after a certain time t0, and typical values for 2 are 0.1 seconds and fitting constant y between 0.01 and 0.02. So, if you keenly observe the overall plots which is represented over here, the plot is with respect to elongation and time t. So, this is a kind of a material response which we observe. However, this is a kind of a desired behavior which is observed experimentally. So, the deviation is denoted as t equals t0. So, the motion amplitude of a bulk piezoelectric actuator remains small. For instance, for the normal mode, the value of d for the best piezoelectric material is in the range of 3.75 into 10 power minus 10 meter per volt. Using the constitutive equation, the corresponding deformation is as a function of the tension U applied on the material and the electrode thickness h. So, this is a kind of a quantified equation which basically talks about the function of tension. Now, for a 1 mm thick material driven at 100 volt, the normal strain will therefore be S equals 3.75 into 10 power minus 5 percentage, which corresponds to a relative elongation of a few tenths of a nanometer. Now, as I had discussed earlier, so we may need to discuss about the amplification principles which are used for piezo actuators. So, if you try to closely observe the amplification principles, there are electrodes which are available and the piezoelectric ceramics which are available. So, this is a kind of an interdigitated structure. The first idea is to amplify the motion amplitude significantly, is to stack up several actuating layers. Doing so, the motion amplitude is multiplied by the number of stacks. A common configuration is to use a structure of a interdigitated electrode. This configuration offers the advantage to amplify the motion without increasing the applied voltage. So, there are wide varieties of these piezoelectric structures. In fact, these piezoelectric structures are efficiently deployed for different applications, which includes a kind of a micro grippers, micro actuators, micro energy harvesters. Even in several cases, it is also used for kind of a micro manipulation kind of systems are being deployed over here. Now, let us see some of the applications of these piezoelectric actuators, how these piezoelectric actuators are deployed for different applications. So, piezoelectric systems are well known for the pump application. So, in fact, wide variety of piezoelectric based pumps are being deployed for different functional applications. This is one such pump where, like, the piezoelectric driven micromembrane pump consists of two glass plate and a silicon disc which is sandwiched between these two plates. So, here the silicon disc is a structure by etching and contains a pump chamber as well as a suction and a discharge valves. So, the upper glass plate serves as a pressure sensitive membrane. It can change the volume of the chamber with the help of a bonded piezo disc. So, which is nothing but an actuator. So, in this particular case, we have a piezo actuator in place. There is a suction valve which is available, and then there is a discharge valve which there, through the suction valve there is an inlet through the system, and then through the discharge valve we can see the outlet of the thing. So, there is a pumping chamber which is available over here, and then there is a microstructured silicon disc which is available. So, this microstructured silicon disc will act as a support structure as and when the piezo actuator actuates, and it is used for suction mechanism. So, when the voltage is applied, the membrane buckles downwards and the liquid is forced out through the discharge valve. When the voltage is removed, the membrane returns to its original position and the pump sucks in the liquid through the suction valve. So, the diameter of the macro prototype of this pump is close to around 75 mm and the thickness is close to around 2 mm. So, the discharge pressure is 0.2 bar, which a maximum of 0.5 bar, and the pump has an operating voltage of 300 volt at a flow rate of 0.6 milliliter per minute. So, the micro pump is able to dose very exactly within a displacement stroke of 0.2 microliters. Now, these kind of pumps are efficiently used for a kind of micro, like for instance for micro lubrications. Sometimes it is also used for biomedical related applications. Next, let us talk about a micro valve. So, as far as a micro valve is concerned, micro valve may have a problem when the external pressure is much higher than the internal pressure. So, acting on the valve can no longer be opened after it has been closed. One solution is the use of a powerful micro actuator which can overcome the external pressure, and this is a kind of a system which shows a piezoelectric micro valve schematic with the schematic. So, the valve is constructed on a glass substrate. A valve membrane is made of silicon by etching technique and it is mounted on the glass substrate by an anodic bonding. So, the actuating system consists of a glass membrane and a piezo ceramic disc. So in this particular case, we have a bottom glass, and on the top we have an actuator membrane glass. Then there is a piezo ceramic disc which is available. So these microstructured wall membrane silicon, and then there is a wall seat arrangement over here. So with reference to this actuation, you can see the overall displacement of this wall seat. So the wall membrane and the actuator membrane are connected with the prism like connecting element. The micro wall opens and closes when the actuator and the wall membranes simultaneously lift or release with the help of a piezo element. So the wall prototype has a 130 micrometer thick actuator membrane with the inner diameter of 10 mm, and the piezo disc acting as an actuator has a thickness of 300 micrometer thick. When a voltage 50 volt is applied, a gap of 4 micrometer can be reached, and these micro walls has a potential application towards drug delivery, towards automotive related applications. Now let me just introduce you to one of the important application area where these piezoelectric systems are efficiently used for micromanipulation related applications. So in this particular aspect, so let me just introduce you to this concept of chopstick gripper. So as far as if you see the overall construction of the chopstick gripper, there is a part of a robotic arm stub which is there. Then there are two fixed base plate, a piezoelectric actuator in the form of a Stewart platform, which is a kind of a parallel manipulator, is placed on both the sides, and then there is an end effector which is a kind of a chopstick which is used for micro manipulating micro materials, or even it is used for micro manipulation of small featured structures, etc. So the very important application area of this piezoelectric actuator is the fine manipulation adjustment of micro objects. Piezo actuators can precisely position these objects with an accuracy of 10 nanometer, and the development of piezoelectric micro hand for micro manipulation tiny objects has been pursued by several research groups for several years. This is one such configuration. So like the main configuration of this is a two piezo driven chopstick like fingers, each having 6 degrees of freedom, are designed to manipulate the micro object like a human hand. The two finger design was specially conceived to work in the micro world where the gravity and the moment of the inertial play only a very minor role. Therefore, two fingers are sufficient for manipulating the micro objects in this particular system. So this has a different orientation and this has a different orientation. Appropriately, these chopsticks are efficiently used for micro manipulation. Now, in addition to this, piezoelectric structures are also efficiently used for kind of optical scanning, especially in areas where you want to go for mirror based micro manipulations or the micro optomechatronics based micro manipulations, etc. Such kind of systems are efficiently used. So in this particular aspect, so a laser scanner integrated with piezoelectric sensors, piezoelectric actuators, has a potential application for different fields. Like in this particular case, so there is a center rod and then there is a piezo actuator which is available. Then there is a mirror deflection plate which is there and a diaphragm and a workpiece and a laser which is there. So what happens is by these adjustment screws, these piezo actuator move back and forth, and these piezo actuator will result in high frequency. These high frequencies are capable enough to deflect the mirrors based on the required system. So what is happening is, so by adjusting the screws, we are trying to limit the overall position. By limiting the position and appropriate orientation of these screws, we can manipulate the laser beam. So here there is a laser beam is coming with the, and the overall force is getting transferred to a diaphragm. So there is a delicate diaphragm which is available over here, and then there is a mirror which is available. The laser scanner hits the mirror, and then by adjustment of the screws, the overall system is kept in tension, and then a piezo actuator is used for a high frequency manipulation, basically kind of a high frequency actuation, so that there is a quite a good amount of displacement. This displacement hits the workpiece, and from there we can try to study the optical receiver capability what we are looking for. Okay, so this is one configuration with reference to laser scanner. The other configuration is a kind of a piezoelectric based micromanipulation. So in this piezoelectric based micromanipulation, how a piezoelectric is used for a kind of a actuation mechanism, especially for the movement of the surface. So here in this particular surface, so there is a kind of ground, and then there is a frame body which exists, and then there is a piezoelectric beam which exists. So what happens is, here the piezoelectric beam is made to vibrate at a very high frequency. When this vibrates at a very high frequency, the vibration is transferred to the frame body, and from the frame body it is transferred to the travelling wave. So what happens is, when it is vibrating at a very high frequency, this vibration is, since it is translated to the travelling wave, appropriately we can see a kind of a displacement which exists. So of course the system will start moving in a forward direction to get a particular reach. Okay, so in this particular case, like this is a kind of a proved technology. So in this proved technology, so this is efficiently used for carrying certain amounts of payloads. Since it has a vibration in place, it has its own disturbance. However, for manipulation perspective point of view, this is a kind of an efficient structure which is employed. Now this system has a kind of a configuration. So in this configuration, let us consider there are two beams are there. So this is a kind of a side view. So as per the side view, we have a single beam, and the beam is going to vibrate, and then it is going to disperse the overall motion of the system. So here in this particular case, so we have two beam structures. So in these two beam structures, so one beam is vibrating at a very high frequency, and the one beam is vibrating at a lower frequency. So one which is vibrating at a very high frequency will try to create a kind of a movement in this direction, and one which is vibrating at a very low frequency will be the axis point for the rotation. So in fact, when this beam is ideal, so this will act as an axis point, and when the other beam is vibrating at a high frequency, there will be a kind of a deflection which exists. Similarly, if we want to rotate in this particular direction, what we try to do is, this will vibrate at a very high frequency, and this will be in the kind of a standstill position, so that this standstill position is capable enough for creating a kind of a different orientation. In case if we need to go for a straight movement, then the vibration should happen at a high frequency in a forward stroke, so that we can sense the vibration, or we can encash this vibration to create a displacement in the forward stroke. In case if we need to move it backward, so we may need to have a reverse frequency, so that there will be a kind of a lift which will be generated. This lift is capable enough to move the system in a backward movement. Okay. Now similarly, this is a kind of configuration where a piezoelectric beam is used. In certain cases, these piezoelectric beams can be replaced with piezoelectric based unimorph or bimorph structures. Now let us consider if I have a piezoelectric beam. So in this piezoelectric beam, there is a kind of structure which is established over here. So this structure is a kind of a robotic platform. Over this robotic platform, we have a piezoelectric structure which is in the form of a piezo leg, and then there is a smooth surface which exhibits. So here, instead of the vibration, it is going to be a single step which is going to exert on the surface. So this single step will be completely like this. So this single step will create a stick, and then it will create a slip. So this stick and slip sequence will result in a kind of a positive displacement over the surface. So that is when there is a platform moment is there, so there is a kind of a stick slip which exhibits, which will result in a kind of a micro manipulation of the thing. So in fact, the distance between this stick and the slip will have a control over the micro manipulation towards the micron displacement which exerts on this particular system. Okay. So this is called as a stick slip based actuation, where there is going to be a kind of a sliding force which exerts, and the sliding force, it's a kind of a ploughing effect or a sliding force effect which exerts, and this sliding force exerts will result in a kind of a movement in the system. Okay. Now apart from this, there is the extension of such kind of system. We can also have a scratch drive arrangement. So in this scratch drive arrangement is concerned, if I have a piezoelectric structure, and if these piezoelectric structure vibrates at this particular frequency, this can be helpful for the movement of these scratch drive structures in a positive direction. So when we closely observe the impact of these positive based scratch drive structures, when the vibration happens, you can have a forward motion. When the vibration is against the drag force, so towards the lift force, then there will be a kind of a reverse motion which we can exit. So ideally, to summarize in a nutshell, so in order to encash this micro manipulation process, so either we may need to encash the frequency, or we may need to encash the displacement. So in this particular configuration, we are encashing the frequency to generate the appropriate displacement. Here in this particular case, we are encashing the displacement to get a appropriate manipulation. So for fine and precise manipulation, this is used. For a large area propulsion, for a longer propulsion, such kind of configuration is used. So overall, so we have discussed about the configuration of a piezoelectric actuator. We have also we have discussed about the direct piezoelectric effect, the converse piezoelectric effect. So we also had a discussion about the various parameters which affects the piezoelectric capability, like one is a kind of a mechanical deformation. Then we have also discussed about the electrical displacement which exhibits. Then we can also so we had also discussed about the overall representation of these piezoelectric structures in the 3D space environment. How does it looks like? And in fact, I have not gone into the detail of the complete derivation of it. So this is just for an understanding. However, when you try to apply it, so it is more on the experimental note, and then like on design perspective point of view, we will be looking into the structural design of it. And then on the constitutive equation perspective point of view, we have discussed about the different parameters which influences the constitutive equation, which includes the strain tensor, the elasticity, the dielectric tensor, the stress tensor, etc. Then we also had a discussion about this generalization of this 3D space. So like we have considered two cases. One is a kind of a short circuit case, and the other one is a kind of a open circuit case. So we also had some discussion about how a piezoelectric polling is done, how polling will have an impact towards the functional applications, and then the response of the piezoelectric structures are basically quantified through the butterfly curve. So this is a kind of a butterfly curve which is being exerted. Hysteresis is considered to be one of the major drawback of a piezoelectric structures. So we have studied the creeping behavior, how an amplification factor has an impact, and then we have seen 2-3 configurations. One is a kind of a micro membrane pump, piezoelectric based, and a micro ball which is available. So a chopstick gripper which is conventionally available, shape membrane, this piezoelectric based grippers which is used for kind of micro manipulating the systems, and then how the micro actuators are used in the laser scanner. Some of the configurations of these piezoelectric based micro manipulations, how it is being deployed, for where we have encashed the vibration and we have encashed the displacement based on the requirement as well as based on the characteristics. The next module we will be discussing about the electrostatic actuators.